Let's say, for example, we need to do a basic reinforcement detailing for a continuous beam given the factored loading or given the factored moment. Let's say we have a continuous beam with hinge or pin connection at ends. Based on the factored load applied to this beam, we get the resulting factored bending moments as shown on this diagram. The diagram shows the maximum hogging moment of 216 kN at the intermediate or internal supports. It also shows maximum sagging moment of 162 kN at the first and at the last span of the beam, as well as a small sagging moment of 54 kN at the center span. A sagging moment is considered to be positive. It is drawn on the positive y-axis of the diagram. It is the moment produced when the beam is deflected in this direction due to the loading, meaning the bottom section is in tension. While the hogging moment is considered a negative moment, it is drawn on the negative y-axis of the diagram. It is the moment produced when the beam is deflected in the opposite direction due to the reaction at supports, meaning the top section is in tension. We will calculate the required steel area based on the factored bending moments. Then we will do a basic detailing of the reinforcement. The material strength of the beam are given as well as the beam dimension. So the maximum hogging moment is 216 kN at the intermediate supports, and the maximum sagging moment is 162 kN, which is located at the midspan of the first and the last span of the beam. First, we do the preliminaries by calculating the value of beta 1 and the effective depth. Beta 1 is the stress block multiplier discussed in my earliest video and is given by this equation. For this example, we will use a 40 mm concrete cover and a stirrups diameter of 10 mm. Stirrups, by the way, are needed for shear reinforcement. For this example, based on the size of the beam, I reckon a 25 mm diameter bar should be good enough. Effective depth is calculated as h minus the cover minus the tie or the stirrups diameter minus half of the diameter of the main bar. So we get an effective depth of 387.5 millimeters. Also, please note that based on the given thickness of the beam, h, the deflection is assumed to be within allowable values, so we will not check for deflection. Next is to calculate the steel area. The steel area can be calculated using the formula ρ times B times D. The ρ is given by this formula. It is the steel ratio. Let me explain how this formula is derived. We know that the formula for bending moment is phi times steel area times the moment arm D minus A over 2. But since the value of A is unknown, we can substitute it by using this formula of A, which is derived from the equilibrium equation. Tension force is equals to compression force. We then substitute the formula for A in the moment equation as well as the formula for the area of steel in terms of ρ. After substitution, we get a resulting quadratic equation where ρ is the unknown. We then simplify the quadratic equation and we get the formula for the steel ratio. We use the strength reduction factor of 0.9 since we are designing a beam which is a flexural member. We want it to be under tension controlled, meaning should the beam fails, it should fail in tension. Also, the steel must fail first before the concrete fails, such that the failure is the ductile failure, not a sudden failure. Based on the bending moment, the maximum sagging and the maximum hogging moments, we get the values of ρ. So we calculate the steel area and we get these values. We get 1677 mm square for steel area required at the supports. Note that this is to be applied on the top section of the beam, which is under tension. We get 1216 mm square for the steel area required at the midspan. Note that this is to be applied on the bottom section of the beam, which is in tension. So if I use 4 numbers of T25 mm bar, I will get an area of 1963 mm square, which is greater than the required, so it's good. And I also check the spacing, which is okay, because the minimum spacing between parallel bars should be greater than the bar diameter. For the sagging moment, I will use 3 numbers of 25 mm diameter bar, which will give me an area of 1473 mm square, which is greater than the required, so it's good. And for the small bending moment at the center span, which is 54 kilonewton meter, I will use 2 numbers of T20 bar. So we will provide 4 numbers of T25 at top reinforcement at intermediate supports, 3 numbers of T25 as bottom reinforcement at the first and the third span, as well as 2 numbers of T20 bars at the bottom reinforcement for the center span. Then for the rest of the beam, I will use a nominal bar for temperature and shrinkage 16 mm diameter bar. So we can also tie up the links or the stirrups. Before we do the reinforcement detailing, we need to run a beam capacity check to ensure that the final reinforcement that we provided satisfies the loading or the given factored moments. You may refer to my earlier videos on how to do a quick beam capacity check. I predefine all the formulas in terms of C, and I just need to input the reinforcement and it will calculate the moment capacity. And it also checks if the steel ratio is within limits. It's a faster way of doing it compared to the conventional way of trial and error, where we first assume that Fs is equals to Fy and then we calculate for C or A. Then if Fs turns out to be less than Fy, then we need to recalculate for C again. So check out the video on how to do a quick beam capacity check using MathCAD. So after doing a quick beam capacity check, the ultimate capacity is greater than the applied loading, so therefore the reinforcement provided is safe. Now let's proceed for the beam reinforcement detailing. Let's first do the bottom reinforcement. So we provide 3 numbers of T25 bar at the bottom for the first span and the last span of the continuous beam, and then the middle span we provide 2 numbers of T20 bars. We can splice the bars and do a tension lap at the supports or just outside the supports, because lapping at the supports is congested. So for bottom reinforcement, we must not tension lap at the midspan because this is the critical area where maximum bending moment occurs. Then for the top section, we provide 4 numbers of T25 at the supports area. And we provide 2 numbers of T16 for the rest of the beam length. For top reinforcement, we must not tension lap at the supports because this is the critical area where the maximum bending occurs. We can splice the bars and do a tension lap at the midspan or at least 1/3 away from the supports. So if we cut sections on the beam, it would look like this. For cut section A, we provided 2 numbers of T16 at the top and 3 numbers of T25 at the bottom. For cut section B, we provided 4 numbers T25 as top reinforcement and 2 numbers T20 as bottom reinforcement. For cut section C, we provided 216 at the top and 2 T20 at the bottom.